I'm Ali Nafisi, and today I'm gonna present the paper Evolving Deep Convolutional Neural Network for Image Classification, published in IEEE Transactions on Evolutionary Computation Journal in 2020. Before diving to the presentation, I want to introduce my social medias on Instagram, YouTube, Telegram, and Twitter. So you can see the IDs below. Some of them are my personal social medias, like those with the ID Ali Safinal, and those that has the ID of AI scientist is for the actually my AI channel. So please follow, subscribe, and join them. And let's start the presentation. So here's the outline. We're going to start with an introduction, defining the problem. After that, we're going to dive into the method and see how the authors of this paper solved the problem. And then we're going to see the experiments, the dataset that the authors used for this paper, and actually graphs and tables. So we're going to analyze the results. After that, uh, we have a conclusion, and the presentation will end. So let's define the problem. To define the problem, we have to specify some goals. So for this paper, I realized that the authors had three main goals. The first one is to do a hyperparameter optimization for the CNN architecture for the task image classification. So they actually didn't try to like use other architectures because it's some kind of hard and difficult to bring all the architecture in the computer vision community into a single representation, single encoding in actually a evolutionary algorithm. So there's a restriction, so they just restrict themselves to a CNN architecture. It's some kind of understandable. So this is the first goal. The second goal is to actually uh, design a proper initialization for weights. So we have some methods like initializing the weights with a constant value or from a distribution or with some prior knowledge like Xavier. But this paper wants to uh, search in the search space for good values, not optimal, of course. This is the nature of evolutionary computation for the weights. So this is the second goal. And the third goal is to reduce the parameters. So uh, the problem is kind of multi-objective. We want to find models that are that have good accuracy, good performance, low error. At the same time, we want them to be like have less parameters, and because the algorithm is population based, we can do a trade-off. We at the end at the final generation we have a population that have some models that have less parameters and comparable like accuracy to the uh, best accuracy models. On the other hand, the best accuracy models have more parameters and maybe they're not a good model for like for mobiles. Okay, maybe our goal is to find a model for mobile, to put it in the mobile, so we have some real-time like face detection or something like that. But this task is image classification, of course. So that's the thing. The authors of this paper propose a model that propose a method that find these kind of models in a population-based approach. Okay, we can categorize the initialization methods into three categories. The first one is just using a constant value. It's very simple, and of course it's not optimal. The second category is to initialize the weights with a distribution, maybe a single distribution or a distribution per each layer. But the problem here is to find the optimal parameters, for example, if we assume that we are using the normal distribution, the sigma and the actually mu are the parameters of the normal distribution. And if we have like 10 layer or let's say 20 layer architecture network, we have to find 40 parameters. And finding those 40 parameters is something that is challengeable. So there's a challenge to find the optimal value for them. So this is a problem. And the third category is initialization methods with prior knowledge, like Xavier initialization. This kind of methods also have their own problems. So at the end of the paper, in the results part, we compare this method's initialization method with the with the Xavier initialization method, which is part of the third category. Here is the whole algorithm of the EvoCNN. So the parts that are bold, these are the contribution of the paper. So what this pseudocode shows is a generic evolutionary algorithm, which we're gonna dive into its details in the next slides. It's generic, it starts with an initialization of the population, and we have a loop that its termination condition, maybe it's a maximum number of iteration, or the actually maximum number of generation, in the literature of evolutionary algorithms. And we have a fitness evaluation step. We specify the fitness of each individual in the population. After that, we select parents from the population. After selecting the parents, we generate offsprings from the parents. Then we have two sets, the population set, the offspring set. We combine them together like a pool, put all of them in a pool, and do a survivor selection from them. So we choose some of them, so the population size doesn't increase or decrease. After the loop ends, we have a final generation with some individuals equals to the population size. Each of them have its own pros and cons. So because the problem is kind of multi-objective, we have some individuals that are good in having less parameters. We have some individuals that are good in having good accuracy, good performance. This is the chromosome structure. As you can see, the length of all chromosomes is not constant, so we have a variable encoding, variable length encoding. Everything is random here. We can have some 2 or 3 or 4 convolutional layers without any pulling layer between them. There may be actually convolutional followed by a pulling layer, after that a convolutional layer. Everything is random. The only thing that is not random here is that we can't have a fully connected layer before a pulling layer or before a actually convolutional layer. So we have a sequence of convolutional and pulling layers. After that we have one or more fully connected layers. So the previous slide was abstract view of the encoding, the representation. Here you can see that each block, either it's convolutional or pulling or fully connected, what kind of information does it have? So here you can see, I won't repeat them for you, but the thing that you have to pay attention to it is that I talked about the problem of initialization. How this paper handled this problem is that it included the initialization parameters into this encoding of each individual. So you can see here, let me just use the laser. Here you can see that the standard deviation and the mean value of, or we can see the sigma and the mu of each layer is separated from the other layers. So we, using the evolutionary algorithms, we search in the search space for the optimal, or let's say suboptimal or good values of standard deviation of each layer and the mean value of each layer. We have this in the pulling layers also, or no, in pulling layers we don't have any actually parameters to optimize, so here we don't have any weights. Here we have some other information, like what kind of pulling layer is it? Is it a average pulling or max pulling, and some other parameters like the height of the kernel. In the fully connected layer, we have the mean value and the standard deviation also. So this is the part that I said we have to actually pay attention to it. Here is the population initialization algorithm, how we initialize the first population. So the inputs is the population size and the maximal number of the convolutional and pulling layers. It's NCP, and the maximal number of fully connected layers, which is N of F. Okay, so the part that we have to pay attention to it is here. When we initialize the N of CP, it's it is just a integer number uniformly generated in this range from 1 to N of CP, which is was the actually from the input. We got this from the input, so we can initialize only one convolutional or pulling layer up to N of CP, and there's a just 15% chance to initialize pulling layer and 50% chance to initialize convolutional layer. So just everything is equal here. After that, we have the second part that we said we actually put some fully connected layers followed by those pooling and convolutional layers. Here also we generate integer in this range, a single integer from 1 to n of f, and at the actually extreme level we can have only one fully connected layer or n of f fully connected layers. Here there's no 15% chance, there's no probability, we have just to specify some fully connected layers. So after that, the population is ready and we return it. Here is the fitness evaluation part of the algorithm. So here we have a data set, we split it into train and validation. We have batch size also, and we have the population. So we evaluate each individual in this population, and that's it. We have a classifier also. We extract the parameters of the actually each individual and build a CNN architecture from it. After that, we train a classifier with the validation part, actually the train part of the data set. We do it with those mini batches according to the norm of batch. After training the classifier, we evaluate it with the validation part of the data set. We evaluate it by actually specifying the accuracy for each for each batch. We have an accuracy. So we have some accuracies that depends on the size of the batch. So after finishing the evaluation, we have to return 3 values. First of all, the n, which is the number of parameters of this network. Then we return mu, which is the mean value of the accuracy. We had many accuracies here because we were evaluating on each batch separately, and because we have not only one accuracy, we have many accuracies, we can compute the mu and the standard deviation from that. And we return those 3 values, so n, mu, and std, which stands for the standard deviation. Here we have a selection operator. So it inputs 2 individuals and it's return one of them as the better individual. So first of all, it computes the actually mu of those two individuals. So we said the mu is the mean value of their accuracy on the validation data set. So it's a check that if their actually difference is not too high based on the parameters alpha, if it's too high, it will return the better accuracy individual, the individual that have better accuracy. If not, if the difference is not too high, so we compare their parameters. We also compute the difference of their parameters, and if the difference is not too high, if it's too high, we will return the individual that has less parameters. If it's not too high, we're going to go to the next step. what's the next step? We compare their standard deviation. So we'll return the one that have uh, less standard deviation because it's some kind of more stable uh, comparing to the second one. And if their standard deviation uh, were actually equal, we just return a random one from those two. That's a rare case, so I don't think that we're going to encounter this case too much. Here is the procedure that we actually do the parent selection. We select parents by this algorithm. So we randomly select two individuals from the population, just random, uniformly random, and we pass those two individuals to the binary selection operator that we discussed it in the previous slide. That function, that operator will return one of them. The output of it is one of those two, and we actually just pass it to the mating pool. We place it in the mating pool. We have a mating pool that we gonna use it later. Here we just wanna fill that mating pool. So this is the third step. We actually repeat these three steps until the mating pool size reaches the population size. So we have some kind of let me describe this point later in the next slides. Here's the algorithm that how we generate offsprings. So we randomly choose two parents from the mating pool that we created in the previous slide. Just uniformly random, we choose two of them. We do a crossover with the crossover operator that we will discuss in the next slides. This will return two offsprings, of course. We mutate those two offsprings with the mutation operator that we're going to discuss it in the next slides. After that, we store the offsprings. Actually, we store those two offsprings, and we remove the parents that we chose from the mating pool, and we do this until the mating pool is empty. So all parents that were selected and placed in the mating pool will be used to generate offsprings, of course. Here is the recombination or the crossover operator that is designed for this variable length encoding. Actually, it's good for it. So, how it's work? We extract the same type layers and put them together, like here the convolutional parts. These are two chromosomes, two individuals, two parents that are selected from the mating pool in this example. So we extract the same type layers and put them together, like here we have the convolutional layers, here we have actually these two pulling layers, and here we have the three fully connected layers. We sort them. We do this also for the second parent, second chromosome. After that, we exchange the values of these blocks. So we exchange the value of C1 with the C1 of the second chromosome. We do this until we reach the end of one of these two. So here we have only two convolutional layers from the actually second chromosome. So this third one from the first chromosome keep unchanged, but the first two will exchange their values. This is also happen for the pooling layers and also for the fully connected layers. That will results with two offsprings. Those that there's a line uh, under the actually text is exchanged value, and here we don't have a line, so this is just kept unchanged. Here is the mutation operator. So we said that after doing the crossover, we will mutate the resultant offsprings from the crossover. So what exactly our mutation will do to those offsprings? We choose a random index or random point in offspring, in an offspring, and with equal probability, we will do one of the following. We like with 33%, we will add a block to that index, and the block will be equal probability, maybe convolutional, maybe pooling layer, or maybe fully connected layer. And with 33%, we may delete that block that we selected with a random number, with a random index, or with a 33%, we may change the values of that block. Actually, we change it randomly, so there's no logic or heuristic behind that. That is the mutation operator. Here is the survivor selection algorithm. So first of all, I have to mention that this is kind of mu plus mu selection. That means that the offsprings that are generated are equal to the current population. So we have to choose n actually individuals. We have to select n individuals from 2n individuals. So that's how this algorithm works. In the inputs, we have the populations, the p, which is the current population, and the q, which is it's the set of the generated offsprings. We have also a parameter gamma, which is the elitism fraction. We will choose some of the individuals just by elitism. That means that we just choose them based on their accuracy. But to keep some diversity in our population, that is something that always we have to consider in evolutionary algorithms and evolutionary computation. So we do this elitism with a parameter, with a fraction, not we don't do it for all the population. That's because we have to keep a diversity. So we choose some of the individuals by their actually accuracy, but for the rest of them, we actually choose in this loop, in this while loop, if you say it, we choose randomly two of them from the population plus the offsprings, and we pass them into the selection operator, that binary selection operator that will return one of them, which is better, and we will add it to the final population that we will return for the next generation. That's the survivor selection algorithm. Here you can see the data sets that are used. By the way, we reached the experiments part, so the method part has been ended. Here we start the experiments part. First, we start by seeing that which datasets are used for the experiments. So 9 datasets are used. They can be categorized into 3 categories, 3 groups. Some of them are related to clothing. Some of them are types of MNIST datasets. You can see that these are 12,000 training image and 50,000 test data. And we have in the third category some datasets that are related to shapes, so rectangle dataset, rectangle image dataset, and the convex set dataset. And you can see the fraction of training and test data of them. That sounds good. Let's go to the next slide. Here you can see some samples from each category, from actually each dataset. That's just to have a sense that what dataset that are we working with, if you don't have the experience with each one of them. Here are the results on the fashion datasets. So let me just have the pointer here. We have 2 results here, best and mean. So what are that? Because of the nature of the evolutionary algorithms, they are completely random. Everything in them is random, is stochastic, it's not deterministic, everything. And by each run, a different actually accuracy will be shown. So in this experiments, in this paper, they did 30 runs for each experiment, and they actually written the mean value of those 30 runs and the best value of them. This is something that usually the researchers do in the field of evolutionary computation. That's why they have 2 rows in this table. So the results are good comparable to other famous methods like VGG16 or AlexNet. We can see that the also parameter size is too low comparing to them, while the error, the classification error, is also low. And the epochs, you can see that what is the epochs number. There's a tricky thing here, that this epoch number that you see, 100, is for the final evaluation. Okay, so in the fitness evaluation algorithm, they didn't do 100 epochs training for evaluating each individual in the actually in the algorithm process. So they did the fitness evaluation part with 10 epochs, and after that, when the final generation returned, they did 100 epochs of each individual in the final generation. Because if they wanted to do 100 epochs for each individual for each population, that would take too much time. too much time and too much resource. So that's also a good strategy uh, worth to mention here. So let's go to the next slide. Here are the results on the other data sets. Uh, as you can see, we have a plus sign or a minus sign or equal sign next to each number. What those means? A plus sign means that the uh, proposed method is better than this method, like for here nnet method. Okay, like for let's consider nnet on all data sets, the EvoCNN is better than nnet. And as you can see, the most values are there's a plus equal next to them, except this one. And like here we have an equal sign, here we have a minus sign. But the most of the cells in this table, I see them plus. That means that the EvoCNN is better than them. And that's amazing, actually. Here we have an interesting plot. So the authors of this paper compared their uh, initialization method of weights to the Xavier initialization, which is a popular one in the deep learning community. And you can see that for all of the data sets, their initialization method had a better performance. So this axis shows the classification error. You can see that in each data set, in all data sets, the classification error of their initialization method is lower than the Xavier initialization method. Here we have another interesting table. You can see that in the final generation, in the last generation, we have a diverse generation. The problem was kind of multi-objective. One of the objectives was the classification accuracy. The second objective was the parameter number of each model. So you can see that here we have 99% accuracy, but the parameter number is too high, like something around a half million, more than half million parameters this model have. But here you see that just by reducing the accuracy 1%, another individual in the last population here, its accuracy, its classification accuracy is just reduced by 1% comparing to this, but the parameter number is too lower comparing to this one. So if you just want to reduce the parameter number a lot, you can see this one here. Its classification accuracy is like reduced by 4% comparing to this one, but it has less than 1,000 parameters, and that's amazing. That's amazing that can each one of these actually solutions can be valuable for us based on what we are trying to do. Do we want to like put this model in a mobile phone or in an application, or we want just to have a good accuracy and the computational resources doesn't matter for us? So you can see that the population-based nature of those evolutionary algorithms help us here. Finally, we reached the conclusion part. So this was a good paper. It had many innovations. It combined the evolutionary computation world with the computer vision world, the deep learning world, and what that was interesting. It had a new strategy for initializing weights. It had a new, actually innovative, novel chromosome encoding method. So it was a variable uh, length encoding method representation. And it designed some mutation and crossover methods to support their representation. And that was also new, that was also novel. And also their binary selection operator, something that was valuable. And in their future work, in their actually conclusion, they mentioned that the future work of their paper can be developing such an algorithm on RNN neural networks. So RNN just a different architecture and maybe needs different structure, different encoding strategy, different representation, different crossover. So, but the idea is the same with this paper, which was on CNN architecture neural networks. Thank you for watching. See you in the next one.